All right, and so we're going to start with this third part of our lecture, our review. So we're now going to this is like a multi-component problem, like it's so many parts. But for a lot of y'all, for y'all who are watching this video and not to the second part, this did show up on my exam. And so to be prepared for something that is this long, I feel like this is the longest it could ever get. But it's better to be over prepared than under prepared, right? All right, so without further ado, let's get started on sketching these graphs. And when we sketch these graphs, Dr. Zhang, if you ever take a Dr. Spiro, Dr. Zhang tends to be a little bit more like these graphs do have values, right? Because these values are representative of your math you solved before and everything that you've seen before. And so, unless in comparison to Dr. Spires, who is more like, oh, sketch the general motion of what this looks like. So what I'm going to do is I'm going to sketch the horizontal velocity versus time and the vertical velocity of the projectile versus time. I'm going to start off with the horizontal velocity. Good. Okay, give myself enough space, so we're good. All right, so this is horizontal velocity versus time. So we have a graph, and then it'll look kind of crazy. It'll be like a lot of lines. That's right. It'll just be like a grid, and then you kind of have to figure out what these values are yourself. I think generally that's what she does. So this is velocity over here, and this is time, right? Time is this way, velocity is up and down. And not just any kind of velocity, horizontal velocity. So I want to go back to what we talked about conceptually, right? When we were talking about conceptual things earlier, we said that the horizontal velocity at the beginning is equal to the horizontal velocity at the end. And a lot of this is because it's going to remain unchanged from beginning to end, right? It's the same throughout the entire motion of the projectile, right? All the same length, okay? So all this means for us is that whether we have 1 second, for 2 seconds, 3, 4, 5 seconds, the entire length of motion, which is the entire 5 seconds, is going to give us the same velocity. So it will simply be a straight line. So let's pretend we're starting at 0. 1, 2, 3, 4. Oops, why is there this thing right here? 5 seconds, okay? So 5 seconds in seconds. And then we need to find that velocity, right? And we said that that velocity, initial is equal to final. And we said that it's 40 cosine 30, which we figured out before is basically around 34.6, which rounds up to 35. And so you can just plot like a big fat line at 35. You just kind of have to make it make sense, right? So 0, 5, and 15, 20, 25, blah, 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 30. Pretend there's lines up here, 35. And all you gotta do is take this and draw a line right here. That is too chunky. Oh, that's still too chunky. Graph a line. Make sure it's from 0 to the end. And that is the length of time. And that is how you plot the horizontal velocity versus time. Okay? Oh my gosh, I just realized they want the horizontal velocity time and the vertical velocity versus time. Dang, this is hard. It's not hard, it's just like so busy. There's so much to be done. So I'm gonna move this. Give me a second, I'm gonna move this stuff. And make it smaller. Make it smaller. Sorry, technical issues. Ignore me for a second. I'm just gonna put it right there. If you watch the video, you know what I'm talking about. All right. So next one we need to do is vertical velocity. And now vertical velocity isn't the same, right? Actually, I'm gonna make this easier to solve, a little bit easier to process. Instead of going to the vertical velocity, I'm gonna go straight to the second component of the question itself, which is the horizontal acceleration of that projectile, right? So I want to project to the horizontal acceleration versus time. Okay, very, very simple graph. If you understand the concepts of what's happening as this ball is going, right? These universal laws. So we know time is on the x-axis, acceleration horizontal is on the y-axis. So what did we talk about? We said initial is equal to final velocity when we're talking about anything left, right, across, right? If if velocity is the same at beginning to end, there is no acceleration happening. If there were a horizontal component of acceleration, we need to get faster or we'd get slower because we'd be decelerating or accelerating, right? But since our velocity is the same, we have no horizontal acceleration. So this graph is also going to be nice and neat. It's going to be 0 meters per second squared. Okay. Just a straight line across. That's all you need to do, right? Stay focused, even if there's a lot of grid lines. So the second part of what I'm going to do is the vertical velocity of a projectile versus time. Vertical velocity versus time graph. So this is going to be a little bit more involved because velocity, as we talked about earlier in the vertical direction, it's changing, right? It's not staying the same. This is 0. It's changing. So our graph is going to have to reflect that. So let me draw a bunch of lines, 0, 1, 2, 3, 5. Bunch of lines, 0, 10, 15. Okay. Pretend I know what I'm doing. Got it? What we're going to do next is we had to think about, okay, let's think about this table right here. What do we start off with for VOY? Because we're only thinking about vertical velocity and we're only thinking about time. So this is 0, okay? So what do we start off with? We start off with 40 sine 30. Sorry, 40 sine 30. That means that is our initial velocity. So if I plug that into my calendar, making sure the mode is in degrees, of course, I'm going to get 20. So whatever I start off with, whatever I decide to be 20, 5, 10, 15, 20, that's where I'm going to start. I'm going to start right here at 20. And something, I'm going to start at 20 at 0 seconds. 0, 1, 2, 3, 5, 6. And that's how long our motion lasts, like we know earlier, right? We also have information to how this ended up, right? Earlier in this question right here, we saw for our final component of vertical velocity. And that final component was right here, not this one in the highlighted, but this one right here, negative 29.78, which rounds to about negative 30, right? So I know that around 5.08 seconds, I'm going to end up at negative 30. So it's like negative 10, 5, 5, negative 10, negative 15, 20, negative 5, pretend I have lines. What my dot is going to end up at negative 30 at 5 seconds. So you can end there and you can just connect those lines, right? And that's all. That's it. You see how all we needed was a VOY and V final Y. And that came from everything we saw before. So now they're asking us to sketch this on an acceleration versus time graph. This is acceleration, the Y, and this is time. What did we talk about earlier? We said that the acceleration in the vertical direction is always going to be negative 9.8. All I'm going to do is do negative 9.8 meters per second squared. All right. And you just have to draw your line right here. Okay. That's all it's going to look like. Okay. So see, looks complicated. It's pretty straightforward if you know what you're talking about. So I hope that makes sense. I think that's a great question. That entire thing was one question. I think it's really useful because it really tests all components of your knowledge, making sure you really know how to work through and logically use kind of a combination of concepts to figure out what equations, how to graph things. Also your math skills. If you know how to find hypotenuse, the sides of a triangle, how to put all the angles together to get your final answer, to get what they're looking for, okay? So what do I have next? Opening questions for chapter 3. Well, since no one is here, there are no opening questions, so just ignore that. I don't what? Okay, then there's no fancy thing that straightens this out for me, unfortunately. There it is. So talented. That was so cool. What we're going to do next is algebraic vector addition, right? This is the other thing that can be asked of you to do. And this is something that you've done before, right? Based off of kinematics, but this is kind of an isolated problem of you having to use the skills. And this is pretty complex too. I'm not gonna lie, this exam, these are complicated units. 2, 4, and 5 3, 4, and 5 are complicated chapters. Hopefully you've practiced a lot up to this point. It's a lot of work, and it really has to have had practice over time. But if you're in the final stretch, you're cramming everything, that's all right too. You just got to be smart about what you're studying, right? And so to study kinematics at when a ball is released from an angle of some point off of an elevated pitch, right? Something where it's elevated, you're not just coming from horizontal ground. But I also encourage you to study how do we get final total displacement from a lot of mixture of components, as you're going to see in this problem right here. So a plane is flying parallel to the ground and it undergoes 2 consecutive displacements. The 2, we have 2, which means we're going to have a final triangle. The first is 75 kilometers, 35 degrees west of north, and the second is 155 kilometers, 65 degrees north of east. What is the total displacement of the airplane? Now, this question always seems easy, but if it seems easy to you, you need to study a little bit more because it's pretty challenging. Or if you're good at math, it's not, right? I'm going to solve this problem in a way that makes most sense to me, and hopefully it'll make sense to you too. So what we want to think of first is the directions. What is happening, right? So I'm going to draw, our little compass. What we grew up with, never eat slimy worms. Whatever you say to make it work. And what they told me was this is undergoing 2 consecutive displacements. This is a 2-part motion, which means that I'm going to draw how I help myself to kind of split this up is to draw 2 axes, right? I'm splitting up this motion because they told me that there's 2 displacements. I'm going to split it up into 2 displacements as well. Okay, so this is the first. The first they told me is 75 kilometers, 35 degrees west of north. I'm sorry I'm speaking so slow. I'm like, it's like a gameplay. It's not. Give me a sec. I'm going to reapply my lip gloss. More seconds. Okay. My lips are not nourished. But let's start with this, right? We talked about this before, 75 kilometers. What I want you to focus on is this really 35 degrees west of north. Do you understand what it's saying when it says west of north? West of north means we start with north, and we go west, okay? Because we're going west of north. We're going northwest, basically. That's a great way to think of it. Think of it northwest. But that's not always going to be the case. So I'm going to urge you to think of it as always start with the second statement and then go west of what they said, okay? So we're starting off north and we need to go west. So that means I'm starting here and I'm going this way, okay? And I don't want to do that color because I want other people to see the difference. So that means this is what's happening, okay? So I'm told Albert went west of north and we went 35 degrees west of north. And we also know that this is 75 kilometers, the actual length of that line itself. So this is good and dandy and all that. you can take this 35 degrees and solve cosine, sine for what's happening here and what's happening here, right? But it's going to be a little tricky. You're going to have to figure out what's sine, what's cosine. What I'm going to suggest and advise to you is to do what the textbook has advised you to do, which is to always take it from the east axis. And this is our east axis, ladies and gents. This is right here, okay? This is our east axis. Always take the angle from the east. And so if you start, put your pencil down at this line right here and just keep on going until you hit that line that you just drew. That is the angle we're going to use. And that is the angle that I will be using for the demonstration for this kind of question, okay? So in total, if I consider the total angle, this is going to be 90 degrees, right? Because if you think about square split into 4, we're going to have 90 degrees. So 90 plus 35 is going to be 125. Because we're taking that right triangle, we're adding that 35 north, west of north, and we get a total of 125 degrees. So that is the angle we're going to use. And this takes the guesstimating out of whether you're going to be using cosine for the x component of that triangle or sine, okay? So what you're going to see is I'm creating myself a triangle. And this triangle don't really make sense, but I just want to draw a triangle so you can kind of see where I'm placing the values. I have A, I have AX, and I have AY. So I'm just going to sketch a little triangle. This is not representative of it. This is just kind of showing you what's happening. So A is 75, right? Kilometers. That's what they gave us. That's the long side of this triangle, the hypotenuse. AX, if you do my method, you always take the angle from the east. You're always going to use cosine to find AX. So this kind of gets rid of whether, oh, am I using cosine? Am I using sine for X? Okay. So if you take it from the east, AX will always be equal to A cosine theta. And in this case, it's 75 cosine 125, which is that big angle, big purple angle, okay? This case, same thing. We're using the method from the east, the total angle. Your AY, you will always be using sine to solve for AY. A sine theta. 75 sine 125, okay? So this is solved enough for us for now. Let's go on to the second displacement. The second displacement is going to be 155 kilometers, 65 degrees northeast. So what did I tell you? Go from east, and then figure out what's going to happen. So it's telling us east, we place our pencil down. They're saying north and east. That means we're going up, going north, right? So some kind of angle like this. 65 degrees northeast. That means this little angle from east to north is 65 degrees. So y'all know what I told y'all before about the whole east thing? Well, you're in luck because this is already from the east. We ain't got to worry about adding no angles, no special treatment or anything. Simply 65 degrees north and east would be good. We're using cosine 65 for our x component, sine 65 for our y component. Okay. So we are also told that this is 155 kilometer displacement. Okay. We rolling, right? So think about your angle again, but I don't want you to think about an A. I want you to think about B, right? B here, this is A here. And you'll see why I tell you to use A, B, because we're going to have a C triangle. Okay. So B right here, B, Y, X. Okay. B, we know it's 155 kilometers. And BX. Because we're taking it from the east, well, it was already nicely provided for us from the east. We just do 155, use this, okay? Use that. 155 cosine 65. 155 sine, sine 65. I'm doing it like a Brooklyn accent. I do not know why. But this is, I hope you can kind of see what's happening at this moment. So we still haven't answered the question, which is asking us what is the total displacement of our plane? So I want to keep it on one page, and then we're kind of running out of space because I just think it's nice to have all your thoughts on one page. I think it's a little bit more easy for y'all to kind of visualize it all on one page. So what I'm going to do is create our ultimate triangle. You remember how I was saying we had A, we had B before? Now we're going to create a C triangle, right? See, this is our ultimate triangle. Draw any triangle, I don't care. Any kind of right triangle will do what you need it to do. This is C, this is CY, this is CX, right? And what we're trying to find is C, because that's what the question is asking us. It's asking us the total displacement of that airplane. But we can't solve for the total displacement of that airplane without thinking about the combined AX, BX, and the AY and BY to make up for CX and CY. So I'm gonna go, I know that was a lot of words at once. I'm gonna break it apart. Okay. So to find this triangle right here, our CX is gonna be equal to our AX plus our BX. Likewise, our CY is equal to AY plus BY. Not that bad, because you already got all the numbers you need, right? You just got to plug it into your calculator or something. So AX right here, 75 cosine 125 plus 155 cosine 65. I'm going to highlight this in blue. Kind of hard to see. So you see where we're getting these numbers? Once you add that all up, from my notes, you should get a value of about 22.49 kilometers. For CY, we're going to be using CY, right? AY, BY, AY, BY. Add it up. Add it up, guys. 75 sine 125 plus 155 sine 65. We're going to get, for my notes, 201.9. Okay. This is nice. We're not at our final answer yet. Remember, this is CX. This is CY. These are our babies, but we still need to put them back in. Okay. Look at this, look at this, look at this, look at this. Okay, just put it back in. I'm gonna go on to the second page. I'm gonna have it pulled up though, so it's not like deadened. No, it's blocking the values. So I'm gonna draw our ultimate triangle again. Part 2. Big triangle. C question mark. CY, which we know is 201.91. CX, which is 22.49 kilometers. So how do we find C? Your old friend that you learned in Algebra 2 back in high school, Pythagorean theorem. Pythagoras. So all I gotta do is take A squared plus B squared is equal to C squared. So remember, any value can be A, any value can be B. It's one of those legs, right? 201.91 squared plus 22.49 squared is equal to C squared. Then we take square root of everything. Provided you do this first, you're going to get C. And that's going to be about 203 kilometers. I plugged into my calculator right earlier on today when I prepped this for y'all. Oh, rude. So that's the total displacement. But if you remember displacement is a little special because displacement doesn't include, just a measure, right? It's not distance. We don't care about distance. We want displacement. And displacement comes, oh, disgusting. Displacement, oh, what the heck? Comes with an angle. So the fun is not over yet, guys. You still have to find the angle. But it's easy. I promise you, if you have all your numbers, easy. The angle you're trying to find is this one right here. Question mark. And remember how we solved it before when we were doing kinematic? Same thing. You want the angle, all you gotta do is opposite over adjacent. Inverse tangent on your calculator. Don't be confused. Don't be overwhelmed by the stupid things that look complicated. They're not. You just need to know what's happening. Opposite over adjacent. You are also going to see this as inverse tangent y over x. And if you want to be a little bit more specific to your situation, cy over cx. Do you see it now? Do you see where we're getting these numbers from? Okay. So what you're going to do is, all you're going to do is plug into your calculator inverse tangent over 201, 391 over 22, 49. And that's going to get you a value of, open up. The heck. It's going to get you a value of about 83.64 degrees. And that's your final answer. 203 kilometers at 83.64 degrees. Okay, so perfect. That's our final answer. So you solved it. If you don't understand this, go over it certain times. As you go through it, the more you practice, you're going to see, I don't understand how I'm getting from here to here. I don't understand where this is coming from. Don't just ignore that, right? Really go into it. Really try to dig into and try to understand why you don't understand what you don't understand, okay? And that's how you're going to learn and get better at this. You have to be able to go in and be able to see this dinner. But anyways, you have to be able to go in and see, like, what am I not understanding? Figure it out so that you can understand when you go to the test. It's not going to magically get better. You're going to have to be comfortable with being uncomfortable so that when you're in the exam, you'll be flying, okay? All right, moving on to the next one. So if you thought that was hard, that's all right, right? I need y'all to go over that. Get the good foundations. Tonight, hopefully you're watching this Monday night so that you can kind of work on chapter 4 and 5 Tuesday night. But if you're not, that's all right, okay? But chapters 4 and 5 really build off of everything you learned in chapter 3. Not just kinematics, but kinematics teaches you how to split up these X and Y axes, right? Which is why it's so important to master that before you move on to chapter 4 and 5 and go with forces, because it all builds on top of each other. And everything you learn about vector addition happens again when you're solving for F-net along an axis and free body diagrams with chapters 4 and 5, right? So what you need to know this chapter is how to make a free body diagram, and that includes being able to kind of find systems, what defines the system, what's in that particular system. When you do these free body diagrams, you should be able not to only draw them, but understand that they're net forces in the X direction, net forces in the Y direction. So that includes being able to split up X and Y axis, and later on factoring friction. I said acceleration equals 0 meters per second squared because as you practice more, you'll see that oftentimes when there is no movement in a certain direction, there's no acceleration. When there's no acceleration, all the forces on the opposite sides equal one another. So that means if you split up into, X, right? Positive X is going to be equal to negative X. Positive Y is equal to negative Y, and acceleration is equal to 0. And it all comes down to understanding F is equal to ma, Newton's second law of motion. And this could be Fx is equal to max. This could be Fy is equal to may. Or this could be equal to Fnet is equal to ma, whatever, okay? It's confusing now, but as I said, the only way that you learn things in physics is through lots of practice and a lot of error so that you can kind of figure out what you don't know and how you can fix it, okay? So let me move us on to our first equation, which is just our first practice problem, which is kind of just figuring out how to draw or clarifying how to draw a free body diagram. So this one says that a skier is accelerating down a slope, there is friction and air resistance. We need you to draw a free body diagram. So when it comes to drawing free body diagrams, you need to think kind of literally, right? Think and envision it in your head. So I'm drawing a scope and I'm drawing a big one because I don't think we need much space. I'm thinking about my skier, right? I'm assuming he's doing a slope. You can draw this kind of slope, you can draw this, it doesn't matter. Okay, you just need to understand what's happening. That's what's important. At the end of the day. Okay, let's go back and not get distracted by me. Okay, so we have a skier person. He's eating, right? Would be okay. Now we need to draw a free body diagram. Right, of the skier. The skier is this free body diagram right here. So he's accelerating on a slope. Oh, see, there's a slope. So I want you to think about this, right? If he is on a hill, what did we talk about in the past when we said anything on a surface will experience this type of force? If you're thinking about a book on a table, it's going to experience a certain type of force, and that force is normal force from that table pushing up on that object, okay? So in the same way, the skier is on a slope. It's on a hill, on a mountain. I don't care. Same way, there's going to be normal force. Normal force is going to be perpendicular. Do you see it? This hill right here. Perpendicular. Not perfect. This should be a right triangle, okay? What next? What we said is that we know that the skier is going this way, right? But it's fine, blah, blah, blah. But there's no arrow going that way for force. At least not yet. I'll show you why our skier is going down, even though there's no force that we can see directly in that direction. What I want you to think about first is that if he's skiing down this way and there's friction against his motion, which direction is friction and air resistance going in? It's going in this way. It's going opposite of his motion. So this is friction, air resistance, I don't know, AR. They don't mean much. You just need to be able to identify them. So what's complex is gravity itself. We know that there's gravity pointing right down. And I don't want you to talk about its opposite normal force. No. Gravity points straight down. Think about you holding your hand, your palm straight in front of your face. Where are your legs? Your legs are pointing straight down, okay? Gravity is pointing straight down, but we don't like it because it does not fit into our beautiful free body diagram, which we want to be like that. We want an adjusted axis for a free body diagram. In order to do this, we need to split our gravity into two components, which is our x and our y, right? So think about it. This is our x. This is our y. So our gravity doesn't fit into neither of those. So we need to make it fit. How do we do this? We split it up into x and y. And once we split it into x and y, the resultant cancels out because the result is a sum and a result of the x and y, right? So think about it, right? This is our FGX. And this is our FGY. Okay, and that result arrow should go from our initial point all the way to our final arrow. So once we do this, this cancels out. And we have this beautiful, beautiful little free body diagram, okay? And I'm going to redraw it for you because I really want y'all to be able to see it a lot better. I always end up redrawing it because I feel like it just works better for my brain without having like this weird thing at the bottom, okay? So air resistance, we have FGY, we have FGX. So at the end of the day, the fact that the skier is moving is, I want you to think about it logically and conceptually, okay? That's what I'm challenging you to do. Is the skier moving up or down? Think about it. Is he jumping up and down the hill as he's going down? No, right? That means our net acceleration in that y direction is going to be equal to 0. Because we're not moving, he's moving this way. He's not moving this way. You know what I'm saying? And so all that means for us is that there is no acceleration up and down because he's not moving. He's not eating anywhere. So acceleration is equal to 0, which all that means is that Fn is equal to FGY. So I'm going to try to make it make sense, okay? This is positive y. This is negative y. This is positive x. This is negative x. That means when I want to find F net y, I'm finding a total sum of the sources in the F direction. For me, that's this, okay? So what I do is I take positive y minus y, right? I do essentially do whatever on the top minus whatever's on the bottom. In this case, it's F normal force minus FGY, which is gravitational force, the vertical component, okay? However, I'm not moving up or down, right? I know that it's not moving. Therefore, we talked about MA, right? That means our acceleration is 0. And if our acceleration is 0 meters per second squared, that means everything goes to 0. That means this entire thing goes to 0. So what happens is you have Fn minus Fgy is equal to 0. What happens if you add Fgy to both sides is you have normal force is equal to gravitational force in the y direction. They're equal to each other, hence why they cancel out, hence why there's no acceleration. This is a very important concept for you to understand, both being able to envision that in X and Y. Now we know that the skier is moving. Back to the problem, we know that the skier is moving in the X direction. He's moving down the hill, right? He's just chilling, he's skiing, which means that whatever this is, Fgx, gravitational force in the X direction, has to be greater than the sum of Ff and F air resistance, right? I'm not going to really draw it out because I really want you to think conceptually about it. Ugh, use that color since we already used it. But think about it, right? F net 0, F net X is equal to whatever's in your, oh, I'm sorry, I wrote this wrong. Positive X, negative X, because you're going down this way. Fgx minus Ff minus F air resistance. It can't be equal to 0 because you have to have some kind of acceleration, right? And so see how we're setting it up. So I hope this kind of gives you the basis for a lot of it. This is very important, so make sure you understand it before you start solving problems. Next thing is that a car is coasting to the right and slowing down. And so draw the diagram of the forces acting in the car. All you need to understand is that slowing down is equal to deceleration. Deceleration is when acceleration and velocity are in opposite directions. Okay, so we have our car, we'll call it stop. Think about it, right? If it's on a road, the normal force. If you're on Earth, you've got gravity. And it says that it's slowing down. So we assume the car is going to the right, right? Slowing down means that if we're moving to the right, our velocity is in the right direction. That means if we're slowing down, we have to